Hi, everyone. Welcome to Virtual Problem Solving Session Week 2. I have chosen not to create new problems, but just to modify your homework problems with different values, but keep the same structure to give you some guidance on how to solve those problems. I think that's going to be more effective because I know you have a lot on your plate this week. This is a heavy 329 week for sure. So before we get started, I just want to say that I think this homework that in particular and what we're going to go through in this video will give you a really good idea of how this class is different than classes you might have taken in the past, because this is open-ended and we're going to go through a process that is very realistic to what you might be doing as a design intern or kind of any internship where you're having to solve something that's open-ended. So let's just jump in. You'll notice this is very similar to problem 1 on your homework. A single reduction speed reducer has 20-degree full depth teeth. A little bit bigger. The diametral pitch is 6 teeth per inch and the face width for both gears is 2 inches. The pinion shaft speed is 1300 RPM. The life goal is about 2 times 10 to the 9th pinion revolutions. The quality index for both gears is 6. The materials are 4340 through hardened grade 1 steels, heat treated to 300 Brenel, or encase both gears. The load is moderate shock and the power is smooth. For a reliability of 99%, rate the speed reducer for power. So how this is different from problems we've done is that you're not given power in this case. You have to solve for power. And that's going to require us to do what I call like your back solving method. So if we don't know power, I'm just going to enter a 1 here. So what we do know is we can figure out the gear diameter, and we have this is the pinion diameter here, the pinion speed, so we can figure out the pitch line velocity. So you can at least get this part set up, but you have to enter whatever you want. But 1 is a good placeholder because you're not going to make a mistake. You're going to know that that's something you need to change. So obviously that's not the final answer, but that's our placeholder. Okay, so if we don't know power, we actually don't know the transmitted load. And if we don't know the transmitted load, then we can't calculate the pinion stress occurring, nor can we calculate the bending stress occurring. So I'm going to leave WT as 1. I have boxed out my other answers because I want you to do that work on your own. Okay, so WT of 1, you can see my contact stress is 4,097, unrealistically low, and my bending stress is 22. What we want to see on this homework assignment is that you're doing this analysis for both the pinion and the gear. You cannot just assume in every situation that the pinion is going to be the limiting gear. You have to check. So you have to show your analysis. Pinion is usually the limiting gear in a mesh, but you have to check. So you'll see that I've set this up. Pinion, gear. Same formula. I'm just going to run 2 different analyses. Again, WT is 1. All right. So let's go to gear strength. We don't know WT, so we couldn't find the stress. We already talked about that. So I'm setting my sigma C allow, which is the contact stress actually occurring, to 1. So again, just a placeholder. And then same thing for the gear. So pinion and gear. And then with bending, same thing. Sigma allow, which is the actual bending stress occurring, set that to 1 for the pinion and for the gear. The only thing that we know is really the only thing we need to know. In this case, the material. So the problem statement says 4340 through hardened grade 1 steels, heat treated to 300 Brenel, core encase both gears. So just like you learned in KQ04, you go to figure 14.5 to find the uncorrected strength, SC. You would get a value of 125,700 PSI with 300 Brenel. And then for bending, the uncorrected bending strength is 35,990 PSI. All right, so we're going to do some goal seeking now. So starting from the bottom, we're going to go data, what if analysis, goal seek. So I'm going to set cell ST to the uncorrected strength value for the material that we know that we're going to be using. So 35990. 35990 by changing cell sigma allow. Okay. I'm going to go up here and do the same thing. Data, what if analysis, goal seek, set cell SC to whatever value is our strength value. Make this a little smaller. 125,700. So let's try it again. Data, what if analysis, goal seek. This to 125,700 by changing sigma C allow. And we're going to do the same thing for the gear. Set cell ST, the value 35990. Changing cell. Notice that we can use the same ST and SC because in the problem statement, it told us that the gears were of the same material. Couldn't do that if you had a pinion that was one material and a gear that was another material. And I can almost guarantee you that is the type of kind of leap you'll have to do for the midterm. No surprises. And then again, data, what if analysis, goal seek, set this one to 125,700 by changing cell sigma C allow. One thing to point out, so you don't make errors. So we were given the pinion speed of 2 times 10 to the 9th. So that is going to be different than the gear speed. And you need to make sure that you account for that in your analysis tool. So all you got to do, so the gear N, it's the pinion speed times the pinion teeth divided by the gear T, because it's rotating slower. So just don't forget that. Because that's going to change your Zn and your Yn values. So let's compare our gear and our pinion, because then we can figure out which is the limiting case, and we don't need to keep doing the gear and the pinion. All right, so let's look at bending first. These values are super close. This is why you need to check. So the allowable stress for the gear in bending, 33,929. So that's the allowable stress, the stress that can be present given the corrected strength value. So we're comparing that to the bending stress that can occur in the pinion, and we're looking for the limiting number. So 33,329 is a little bit smaller than 33,929. So far it looks like the pinion is the limiting factor. And then again, we do it up here. You should see a greater difference with contact, and we do. So the amount of contact stress that could occur in the gear, given our material choice, is 114,128 psi, and that is higher by a little bit than the allowable contact stress that can occur in the pinion, given our material choice. Okay, so we can conclude that the pinion is the limiting factor. So that already gives us a clue to the design solution here. So when we're rating this system for power transmission, we need to make sure that we're only passing an amount of power that's not going to cause the stresses to be too high in the critical gear. So the pinion is what we're designing for. So now we're going to look at the gear stress. So we're one step closer to finding the WT, and then we can back solve to find the power. So we need to limit the bending stress in the pinion to, what did we get? 33329. Again, where did I get that? From this cell right here. We need to limit the contact stress to 111281. Where did I get that? From the cell. Okay, so we're going to goal seek again. We're going to set cell F56 to value 33329 by changing cell WT. So to not exceed this allowable bending stress of 33,329 psi, we would need to limit the transmitted load to 1,490.5 pounds. We do the same thing for contact cell. Data, what if analysis, goal seek. We want to limit this cell to 111,281 by changing WT. So that's a lot lower. $737.8. So it looks like our limiting case is the pinion and wear, and here's our limiting transmitted load. Really common error I've seen is you want to, for some reason, pick the higher transmitted load, but that is exceeding the capacity of the gear's strength. So you want to go with the lower transmitted load. Okay, so now we need to limit our transmitted load to 737.8. So goal seek again. We're going to get so good at goal seek. This value 737. So there's your final answer. The power rating is 25.36 horsepower. Problems 2, 3, and 4 are going to be a lot easier once you have problem 1 under your belt. So problem 2, speed reducer in the previous problem is to be used in an application requiring 40 horsepower at 1300 RPM. For the gear and the pinion, estimate the AGMA factors of safety for bending and wear. By identifying the factors of safety, identify the threat to each gear and to the mesh. So everything's the same here. We've entered in 40 horsepower, which has yielded a new transmitted load. And then that transmitted load, input down here, input over here, giving us new contact stress values and new bending stress values. So I'm just going to bring these values down to the strength equations. So nothing fancy, just referencing those cells. Here, here, for contact, your pinion on the left, gear on the right, pinion bending, gear bending. Okay. So in this case, the uncorrected strength values have not changed. So these are the same from last time. The hint here is to set your factor of safety to 1, and then you're going to goal seek to figure out what would your factor of safety be to meet the capacity of the gear with the given material. So data, what if analysis, goal seek, set this cell to 125, 700 by changing this factor of safety cell. In this case, we actually have a material that's not going to meet the wear demand for the pinion because the SH is less than 1. So you perform that analysis for all 4 cases. Just make sure that you are calculating the SH squared value because that's what you compare to SF to determine what the threat is. So you're going to determine is bending or wear a threat to each gear. So in this case, probably going to be wear, and then to the overall mesh. Problem 3, the gear set in the previous problem needs improvement in wear capacity. For this end, the gears are nitrided, so they have new hardness values. Both the pinion and gear cores are 250, and their case hardness is 390 Bernal. Estimate the power rating for the new gear set. So you're going to redo your analysis for problem 1 by finding SC using 390 Bernal. Keep the bending ST the same. So we haven't changed anything to the core of the gear. We have only hardened the outer shell or the case. So specifically, this value is going to change. So you're going to use 390 for now. Problem 4, now reduce the physical size of the gear set by 1/2 and note the result on the estimates of transmitted load and power. So if we want to decrease the size of the gear set, your tip is to consider how you're going to do that through this relationship. So what effect does reducing the diametral pitch by 2 have on D? How does this impact the estimated transmitted load and power?